So I'm gonna summarize what I've studied in chapter 12 so far. So basically it is about atomic physics or something, nuclear and particle physics. So an atom is basically made of electrons, protons, and neutrons. Now there's a center of an atom which is obviously called the nucleus, and you guys would have heard about that, so there's nothing new. And protons and neutrons are the nuclides because they're present in the nucleus, and then we have electrons revolving around them. Now protons and neutrons have mass and electrons don't have mass. One thing that defines the identity of an atom is the number of protons it has. Like if you have six protons, then you're a carbon atom. But if you have seven protons, you're not a carbon atom anymore. You are a neutron atom. Sorry, a nitrogen atom. So proton is rigid, which means it defines that what is the identity of an atom. Now atoms with same number of protons and different number of neutrons are called isotopes. So this is how we categorize the atoms, because if it had different number of protons, then it won't be in the same category. It's completely different atom. So isotopes are the subtype of an atom or an element that have the same number of protons but different number of neutrons. You can have a certain numbers of excessive neutrons in an atom before it starts to decay, because then it gets unstable. Now in carbon atoms, if it has 6 protons and 7 neutrons, it's still okay, it doesn't have a problem with that. But when it gets 6 protons and 8 neutrons, then it has a problem. What happens is that it starts to decay, and it takes it 5,730 years before carbon 14 turns into nitrogen, and it converts its one neutron into proton, which is called alpha decay. Now this is called the negative alpha decay, and it releases obviously it converts the neutron into a proton, but also an anti-neutrino, and it emits electron to conserve the momentum and energy. Now this electron is called the beta particle, and this process is called beta decay, and in specific positive beta decay in our case, because it converts neutron into proton. Now for lots of years and lots of period of time, we thought that protons and neutrons are the fundamental particles and they can be divided into more categories. But we have discovered that when scientists look deep into nucleus and they try to collide protons and neutrons with each other, and trying to convert them into subatomic particles, further they discovered that they could find lots of new subatomic particles, and they named every subatomic particle except for proton and neutron mesons. Okay, so anything that is smaller than proton and neutron is eligible to be called a meson, and then it has its own name. There are millions of new subatomic particles. So the main particles that we're going to talk about are quarks. Okay, quarks and proton and neutrons are made up of quarks. Now proton is made up of 1 up quark and 2 down quarks, while a neutron is made up of sorry, a proton is made up of 2 up quarks and 1 down quark, and a neutron is made up of 2 down quarks and 1 up quark. So we'll get to the details of it later, but for now just understand that protons and neutrons are made up of quarks, and proton has 2 up quarks and 1 down quarks, and neutron has 2 down quarks and 1 up quarks. One thing about quarks is that they don't exist isolated. They always exist in groups, or at least a pair of 2, and when you try to separate them, you put up enough energy that the energy gets converted into additional 2 quarks, and then you can really separate them. So now we're going to talk about the fundamental forces that hold our universe together. Now, the 2 basic forces are gravity and electromagnetic forces. Gravity is basically the force that makes things fall down from Earth, and it acts over infinite distance. It is very weak, but it is directly proportional to the product of masses. So that is why on Earth, the mass of Earth is very strong, so we feel it very strongly, and it is always an attractive force. It does not exist, or almost doesn't exist, for atomic particles at an atomic level, but for stars and etc., obviously it helps in the revolution of planets around stars and stuff. Okay, now electromagnetic force can be attractive or repulsive. It binds most of the things together. Basically, positive and negative attract each other, and same charges repel each other. So it is a very strong force. It is responsible for a wide range of physical phenomena like chemical bonding and other stuff. Strong nuclear force. Strong nuclear force exists for atomic distance level. At atomic distance level, now what happens is that it holds protons together despite them being of same charge, so it overcomes the repulsive force by the strong nuclear force, so it causes the stability of atoms. Now weak nuclear force is responsible for beta decay, when it helps one proton getting converted into neutron and 1 neutron getting converted into proton. Now Paul Dirac said, now this is another topic, its name is matter and antimatter. Wait, let me change the pages. I was just reading from my notes. Now Paul Dirac said, for every matter there has to be an exact copy of it, and it should be exact. It shouldn't be like any compromise. Like you could say electron has a negative charge and proton has a positive charge, so they're copies of each other, but they have different charges. Now they have the same mass. Okay, now for every matter an antimatter and its twin should exist. For electron, it is positron and it has the same mass, like I said, but with different charge. For proton, it is antiproton. For neutron, it is anti-neutron. For neutrino, it is anti-neutrino. Now, the first one that was discovered was positron by Anderson. When matter meets antimatter, basically what happens is that they produce a lot of energy and they just disappear into thin air. Now, considering that each fundamental particle has its antimatter, we are doing some experiments to prove that. Now, what we're gonna do is called pair production. What happens is that we pass a gamma ray near the nucleus of an atom, which has the energy equivalent to the nucleus has the energy equivalent to 1.02 MeV, and the reason for that is that in order to conserve the momentum, we need to have the exact amount of energy that the antimatter and the matter that we are creating would have. So basically, we pass a gamma ray near the nucleus of an atom. It gives a bump to the nucleus, and the electron as positron gets created. It can only happen, like I said, it can only happen when in the presence of a third particle called the nucleus, and the energy it should have is 1.02 MeV. If it's less than that, it won't occur. If it's more than that, it would get converted into the kinetic energy of positron and neutron and an electron. Now, the energy that we are giving the nucleus gets converted into mass, which is according to the Einstein equation, E is equal to mc square. Now we're gonna do an opposite of this, and that would be annihilation. Annihilation is obviously an exact opposite of pair production, where matter gets converted into energy. We were doing what is that we were converting energy into matter, but now we are converting matter into energy. What happens is that they take a proton, they take a positron, they make them collide with each other in opposite direction, and then boom, we have two beams of light, each containing 0.51 MeV of energy, and they just disappear into thin air. And also at CERN, you would know that at CERN they turn mass of colliding particles into energy, which proves the E is equal to mc squared theory, and leftover mass gets converted into subatomic particles. And this is how we discover a lot of new things about the nature, which we'll also talk about in later topics. You could read this and get your information better. Okay, pair production, the input is high energy proton, the output is electron plus positron. Annihilation, the input is particle plus antiparticle, and the output would be two photons, mutual interaction. The requirement for that would be, and for pair production, the requirement would be proximity to a nucleus, and at its equations, high velocity gamma particles, radiation plus new particles, extremely high kinetic energy. Okay. Now we're going to talk about radioactivity. So the thing is that everything in this universe wants to get stable, and in order to do that we need to make some compromises, and we need to maybe add or remove things from ourselves. Now, radioactivity is basically the decay of atoms when they're unstable and they want to get stable. For every atom that has more than 82 atomic number, they emit radiations to get stable. Now, scientists in laboratories, in order to do experiments, what they do is that they they take a completely stable atom and they bombard some particles like alpha particles or stuff like that on it, and it produces stuff. Okay, now we're gonna talk about the most complicated of all. Till we have the most complicated among all the topics we have covered yet. The types of radioactivity, which is alpha decay, beta decay, positive beta decay, and negative beta decay. So let's begin. When an atom gets atom in the process of radioactivity throws out some sort of stuffs, and these stuffs are like three of these stuffs. It throws three stuffs. So an atom in alpha decay, an atom throws out a tiny clump of 2 protons and 2 neutrons stuck together, and because it has a positive charge, the magnet pushes it a little to the side. It goes pretty fast, but it's heavy. It gets tired quickly. It can only travel a few inches in the air before stopping. Now, what happens in alpha decay is that an atom is too crowded with alpha particles. It's too crowded with protons and neutrons that it starts throwing out 2 proton and 2 neutron for alpha decay. Now the problem is that it is too crowded, right? It's not like we have an even number of protons and neutrons and we want them to get converted into one another, but they're just too many, so we need to emit them out of the nucleus. Now they throw 2 neutrons and 2 protons out of their nucleus, and then is equivalent to a helium particle, which is again the same 2 neutrons and 2 protons. The mass number of that would be 2 plus 2, 4, because it's 2 protons and 2 neutrons, and the atomic number would be 2, which is 2 protons. So that is the case for it. And what is beta particle? Now, what is a beta decay? For alpha decay, the helium particle that gets extruded or emitted is the alpha particle. For beta decay, the problem is that we have uneven amount of protons and neutrons in the nucleus, so we can either convert, if the number of protons is too much, we could convert a proton into neutron. If the number of neutrons is too much, we would convert a neutron into a proton. So in positive beta decay, what we do is that the neutrons are too much considering the amount of proton in the nucleus of an atom. So a neutron gets converted into a proton, but it also emits 2 different kinds of things along with it. One is an electron with a negative charge on it, and one is the anti-neutrino. Now, anti-neutrino is the antimatter of neutrino, which is just neutron without being in an atom, but just as a radiation, which isn't really a thing. It's just a thought. Like, it doesn't really matter. Sun passes thousands of neutrinos, and they just pass through our skin without touching an atom. So that's it. Beta positive decay is when a proton gets converted into a neutron. Now what happens is that the atomic number decreases, but in negative beta decay the atomic number doesn't decrease, it gets increased and the mass number remains the same. So the mass number in both of these remains the same because we're just converting one atom into another. So the only time where the mass number would get affected would be in alpha decay. So a proton gets converted into a neutron and it secretes or emits a positron, which is the antimatter of electron, and neutrino. Okay, so we are converting a proton into a neutron and it is emitting positron and neutrino along with it to conserve the momentum. So this is what alpha and beta decay were. Now gamma radiations means when the gamma rays gets emitted out, they don't really have a mass or anything, they just pass out. Okay, so now we're going to talk about the fundamental particles. And the thing about fundamental particles, which I talked about earlier in the video, in the start of the video, was that scientists at CERN did more experiments and tried to divide the protons and neutrons into subatomic particles and found out there are more particles than we thought there were. Now there are two types of even smaller subatomic particles. The family one we would call are quarks, and the family two would be leptons. Now quarks are the particles that feel strong nuclear force the most. They are incredibly sociable. You never find one alone. They always hang out in groups, clumped together by the strong force. What do they make? Okay, so basically when quarks stick together, they form groups, and the groups are called hadrons. There are two types of hadrons, baryons and mesons. These are made of three quarks. The most famous ones are protons and neutrons. Two up quarks and one down quark is proton. Two down quarks and one up quark is neutron. Now the second type is of hadrons, which are the type of quarks, is mesons, called the messengers. They are made of one quark and one antiquark. They are lighter than baryons but are very unstable, decaying into pions and kaons. Pions and kaons are the examples of mesons that hold them together as a glue. Now, if a particle feels strong force and is made of quarks, it's a hadron. Hadrons are either baryons or mesons. Okay, now family 2 is leptons, the loners. Leptons are the other fundamental family. Their name comes from the Greek word small or thin. They don't feel strong nuclear force because they are truly secluded. They don't clump together to form bigger particles like quarks do. Examples of these would be electrons and neutrons, the one we met in neutrino and electrons. Neutrino is basically the one we met in beta positive decay. So yeah. Now leptons also have anti-leptons because every matter has antimatter. When scientists were using particle accelerators, they didn't find just quarks and leptons. They find over 100 other particles. The strange particles. Some of these particles, like the kaon and the lambda, behaved in the weird ways. They were easily created in collisions but decayed very slowly. So this was or that physics called them strange particles. Remember the names kaon and lambda. They always existed in pairs. For example, when a pion collides with a proton, they create a kaon and a lambda particle. This conservation of strangeness is a key rule in particle physics. The spin and the two personalities, fermions and bosons. All particles have a property called spin, which is a tiny internal angular momentum. It's not that they're literally spinning like tops, but they have a fixed amount of this intrinsic twist. Spin value determines their whole personality. I will explain the further more details in the next video.